Добрый вечер, уважаемые коллеги.
Good afternoon, colleagues. I'm Alexei Horoshilov from the Institute of System Programming of the Russian Academy of Science, and today, in my presentation, I will try to share my experience about testing and verification of the Linux kernel, and not only it. In the framework of my presentation, I'm tell you about a few our experiments about using advanced verification methods of the operating system kernel. The first project was the software model checking, which we started 15 years ago in the middle of 2000, when the tests became more mature. It can be applied to good programs. When we started using them in some projects like Microsoft Research, SLAM as the instrument got into Windows driver development kit. It was interesting how to use that methodology to the Linux kernel, and that's what we did. Let me comment about software checking, static checking. We try to analyze the code and to find out whether there are some errors in the code or whether errors are not present. An error is a wrong state of the program, and the tool is looking at the injection point to a certain erroneous state. The idea of model checking were used for quite a long time, but they were not applied to the applications, to software program, because the code was very complex. And somewhere at the end of the 90s, the idea was born about automation of the analysis without human interference. The ideas were quite simple, nevertheless, they worked. The main one was the counterexample, the CGAR summary, as we call it. It works like this. We cannot build and analyze the complete model of the program. We can build a rough model with only part of the contents present. But if we do it conservatively, we can check it. If this simplified model is okay, then the real program is okay as well. But if we failed to do that, then it means that we found something which brings the program to a false state. Going along this way, we can build a complete model and check whether the way that we found can be realized or not. If it can be found, then we can offer it as an error, a bug. But if we don't find the way, it means that the rough model doesn't include some essential elements which close the gap. CGAR tools use different heuristic algorithms, and it really works. Now, what if we try to use that tool to Linux kernel? About 30 million lines of code. First, what are we going to find? What are the typical bugs, typical errors. We made an analysis of all commits which got into the kernel in a year and found typical errors that were corrected later. Not the bugs in one driver, but the ones which can be found in many areas of the code. So statistics shows us that the typical bugs are related to internal API, incorrect usage of the Linux kernel API, about 50%. The second is generic errors for all C-based software pieces. And the third one is the synchronization errors. So it helps us to find out what are we going to look for in the kernel. The tool to analyze was a CPA checker, the open source tool developed by a person from Munich University. We joined the team of developers, and then some other people joined the team as well, and we tried to use the tool for the project. If we try to apply that tool to the operating system kernel, nothing will happen. We have to find realistic pieces and analyze them piece by piece. For a kernel, we can divide it by the borders of the modules, but actually sometimes we have to take several modules at a time. So that's what we did. Then what are we going to do? If we take not 30 million lines, but about 1,000 lines, what do we expect? We expect the entry point and the error location, something like assert, which shows us, well, we don't see any function here. We saw the init module, which says that this is the function which calls for a certain structure registration, and there are functions of the next level. You can register more functions. So naturally, when we see that, we have to build a simple model that will call the initialization function and look at and emulate the way the module operates in the kernel. We do it, but there are some subtle things you have to take them into account. For example, you don't have to call them at random. There are different, not always obvious dependencies. One function should work 100%, and then only you can call the other one. And each type of the kernel has its own specifics here. When we looked at the picture, we saw there is a chart in the right bottom kernel. We have about 700 modules, but 70 to 80 of them cover about 70 to 80% of the total. And you have to focus on those 70 ones. Still, this is the problem, because you cannot analyze all the modules in this way. And the task is to build a model of the environment that will try to find a compromise between three targets. First is completeness, not to miss any bugs. Then it should be simple and correct without finding false ways. And well, if you honestly describe everything in detail, then it wouldn't be simple at all. So you have to find the golden middle between these three items. We solved the first task. We have an entry point which understands the verification tool, and you can run it. Where is it going to find the error location? For C-based programs, you don't have to do anything. The analysis is done automatically. Very often we have incorrect usage of the API, but it cannot be checked. What we would like to have here, for example, a code, it calls a certain function, location, and unallocation of URB, and we would like to support information about resources allocated, URB in this case. And when we call free, we have to check that the parameter is null or previously allocated URB. And in the end, we can check all the URBs that were called, and they are all deallocated at the end of the work. This is a workable idea, but I cannot show you how it works. If I try to describe it without showing you the slide, of course, I would like this thing to be supported in the model, and the asserts should appear automatically. It resembles aspect-oriented programming. When code is added from time to time into the program analyzed, and we have tools for source-to-source transformation, but we didn't have anything like that available in open source. So it worked in our system as aspect-oriented description, and here we add code that works with the model state and different assertions. As a result, we get a modified code which contains everything that is needed for us to check the availability of erroneous error locations. It's an instrumentation framework on the basis of C, and as a result, we solve the problem and use that tool and see what happens as a result. If we show you the picture as a whole, this is our framework for the kernel drivers. These are all the stages. Clade, what kind of code is in the kernel, and where you can see the borders between the modules. Then decomposition for the sections to be analyzed, then generation of the environment model, instrumentation, verification, and analysis of the results. Of course, a human being cannot analyze it easily, but we added some web interface features which shows you the green, the red lines, and easily analyze the code. We can even see whether it's false positive or not, and in the next version of the code, and those ideas will be used automatically. Positive things: the instrument works, the tool works. If you look at the repository, we found about 430 patches, but in fact the situation is more complicated. For example, two classes: reachability, the approach of incorrect usage of API, and memory safety, typical errors. The statistics is different. We found errors. So in the second line, that absence of the error is proved. 83% seems to be very high. So in 83% of the drivers have no errors, which is wrong. The statistics here is more complicated. We checked 20 rules. Then it's the statistics about the number of rules and the number of drivers. It means that in 83% of cases we proved that this rule is not violated in this particular driver. It doesn't mean that 83% of the drivers operate without errors. And actually in 17% there is no result, 42% no result. It means that within 15 minutes that we allocated, the tool didn't do the job completely and didn't produce any result at all. If we looked at the bugs that we found, how many false positives and true positives are there? False positives in reachability about 65%, in memory safety about 90%. Too much. Nevertheless, if we look at the reasons, actually, the verification tool produced comparatively few positives. Most of them go from the environment, which means that we have to do more about specification of the rules. Without any fanaticism, if we go into great detail, then you will get to the no result line. Let's go back to the previous slide. The result is not bad at all. The tool works. The tool helped us to find a lot of bugs. We used it in different modes, including For 7 or 8 years, several students under the Linux Foundation auspices prepared patches, used this tool. Not only our students, there was one Egyptian and several Hindus, a girl, very talented. We praise her for high quality of work. And what is the result? What is the outcome? The method is workable, applicable, and it produces good results. The next project that I would like to describe is the deductive verification of Linux kernel. I am not going into great detail because Denis Yefremov have been talking to you for several years running before, and he discussed everything I showed you now. He is in charge of the project where we try to use the open source tool to the components and demonstrate deductive verification for simple functions. But in reality, of course, the main area of application here, because it's a heavy and expensive module, it's the most critical part of the kernel, which supports the most critical function, proprietary code, which is implemented by our colleagues. For example, LSM modules for security policies. Denis didn't tell you about this point because the bug was disclosed before he joined the company and wanted to show it to you. It was found by Moscow University students when I delivered lectures about the formal methods. So these are the simple functions, and they found a real bug in the Linux kernel. The function which gets the set from the range, cleans it, and gives back and returns the number of elements after the cleaning with appropriate triaging. The problem appeared when the range was filled 100%. And what has to be returned? The first empty symbol, but if there is no empty ones, the set returned 0, which was not correct. And all the data that could be there in that set were lost. So we sent the patch. The patch was accepted immediately. This is a functional area, the example of the functional area, which would be difficult to find by other methods focused on typical bugs, typical errors, only if it wouldn't show itself later in some other areas. So at this point, I would like to go to the third example of our experiments, and this is testing on the model basis, based on models. I'm not talking about kernel exactly here. We tested here something which is described in the Linux standard base. There was an initiative about 13 years ago trying to describe the binary interface, which is common to all distributions of the kernel, although by extending the digital signature at Linux, I launched our products, and it was written in standard OSB, and I was happy because there is no standard OSB. It didn't work it wasn't accepted broadly, although Siemens started using it, and they generated binary codes which can be used between different distributions, regardless of the they are common for all of them. And we have GLFC standard here. We also related to POSIX because they were there in most cases. In that project, I want to draw your attention to three ideas which were quite bright. The first one is that when we have a standard and a set of requirements to be checked as plain text, those requirements should be systematized and classified. So we built a catalog of requirements for the standard in the browser, in the text format, and each piece had an identifier to facilitate checking and verification. As a result, we generated a template of formal specification. This is the second idea, which would be interesting. We tried to formally describe the requirements to interfaces of library functions in GLFC. We can see that we have identifiers taken from the standard template, and if we apply certain code here, that would check memcpy, and I wanted to check parameters, that the parameters are really valid. They are pointed to actual sections of memory, and they are not intersected. It looks strange, although it's almost C. It's our proprietary extension of C used here. The word on top is related to the fact that our description is external from the function. If the function is called here in this machine, in a certain process, in a certain flow, it will be done through certain agents, but where specification is going to work in Oracle will define whether the function is correct or not. This is a different machine, and the call context is described in that way. We describe the area where it is called and where it is executed, and they are different. These are the parameters that were sent to the real function. The preliminary condition is what is allowed to be transmitted, to be sent. Let me show you the post conditions. Yes, this post condition is missing. But as you can realize, in post condition, we describe what we expect in the end. The memory is going to change as a result of copy. It is not going to be changed in any other places, and the returned result will match the specification.
So based on that, we can automatically generate the oracle, that is the code that for any call of the target function would test whether when called the function worked as intended or not. But because such a test can be done for any input parameters, this opens up a broad field to generate testing sequences for functions in various states with various parameters. And this uses the third element that I wanted to draw attention to. This is generation of test sequences that was implemented in this project. And it describes mini scenarios. There would be mini scenarios of sending messages, reading messages, maybe consisting of several actions, and we put this into a mini scenario bucket, and we describe an abstract state that we are in a certain state in the tested system. If we test a queue, for example, that could be queue length. And then the engine starts taking the mini scenarios from the bucket, checking the state and applying them. And it does automatic enumeration so that in the tested system we progress from one abstract state to the next and then to the next again. And the objective of the engine is to make sure that in every abstract state that we reach, every scenario from the bucket was implemented. So if we went quite far in this part, but we still have outstanding scenarios in other parts, then the engine would go to that other part, to those other mini scenarios, and would continue enumerating new scenarios there. To demonstrate that we have been able to find some non-trivial things, let me give you an example of a bug that we were able to find in the MQ system. And it's one of the cases that would be difficult to find for a tester in a sound mind, so to say, but the automated tester was able to find it. So from various flows, descriptors are created to the message cube, and one flow sits in send, and the other flow closes the file descriptor. So when receive happens and send should initiate, the flow that uses invalid file descriptor gets an alert. Now, this is a good operation, but the problem was that if there was another flow for send, it would be stuck forever. This is not the only bug that we were able to find. If we were to look at the project statistics, during the catalogization, we found some bugs in the standards, we found some bugs in the glibc, and we fixed them. And Udi Draper was the maintainer of glibc at the time from Venus Foundation, with whom we worked. We're surprised that he actually accepted this bug report from us. This method proved to be interesting and quite effective in a way. Testing that aims at investigating thoroughly a particular code. This approach turned out to be quite useful, but it turns out that it's difficult to work with developers if you give them this distributed structure test and show them that there's a crash. So if it's one call that crashes, then it's okay. But if there's a long chain that has to be followed to understand what the problem is, it takes investigation into the testing system, and not all developers can really work with it. And so it's not as straightforward as with simpler tests. And because of that, and maybe also because it's quite difficult and expensive to write such tests, so when we started to work with that foundation to cover not just the XP core part, but also the other part, including the desktop part, we followed a different path. So we did another type of tests where we did tracing. The tests were more straightforward with inbuilt assertions. We used parameterization when many tests were generated using the same template. And we developed tests for a bigger number of libraries and in less time. But that was not a very novel in terms of science. So we saw that we wouldn't be able to, even with simple tests, to go through that in adequate time. We thought, could we do a test to understand that the system is workable? Because that became part of the certification test kit in OSB. And we wanted to have tests that would indicate that things are going well. So we decided to do tests that do minimum checks. And the idea was for us to generate tests. Well, headers are not sufficient. We needed to add some more substance. So we added some manual descriptors. And the descriptors featured information that couldn't be extracted from the header, such as, for example, how to analyze the library to call functions, how to get appropriate values of certain types if that was not a trivial task. And if the method had any specific features, that could also be described. So this is how it looks. So we either generated an object automatically in a particular place, called a particular function with an automatically provided set of parameters, and this could help reap some benefits and to generate functional tests with reasonable effort. And this worked with libraries which are quite big in terms of the number of functions, and such as Qt.xml and well, with the smaller libraries, you don't get a lot of benefits because you would have to write an individual test for every function. But here, because of scale, we were able to generate some simple tests, and they found some errors, amazingly. That was somewhat random, but still, they found it. But importantly, we achieved our main objective. We were able to come up with tests that can check the functions in a distributive. And I guess the final project that I wanted to touch on briefly, that's when we'll go back to the kernel and see how we can test the code that's responsible for error detection. This is something that developers don't like because it distracts them from their core business. It's difficult to keep things in one's head, so this code is hardly being tested. And in fact, it hasn't been an easy thing to test for a long time. And because it's it is very seldomly used, and if it's used, then developers don't get a lot of feedback, so not a lot was done about it. So we thought how we could test this code on a systematic basis. There is fault injection, and when we did that, some of it was used for the kernel. But the only mode that was supported was random error generation that we had some concerns with, because we didn't want to rely on a random process. We wanted to come up with something more systematic. As a target object, we selected the file systems and we tried to work with them because that was simpler, and also it turned out to be quite useful. In terms of error emulation, we created mechanisms of thematic enumeration of failures. In the initial run of the tests that we thought would run deterministically every time, we collected information on all the potential failure points, and in further executions we automatically enumerated where the failure could be introduced. If we were to compare this with the set of experiments that we did with the simple randomized approach, okay, so the baseline here is the test time was 2 minutes. So in the middle we have randomized enumeration, and the bottom two lines were systematic enumerations, when we only took into account the stack of the failure and previous stacks. If we were to assess the effectiveness, the performance, systematic approach demonstrated good performance. It helped find issues, but then there were some problems with that related to double failures. Okay, some errors were found, but I understand that I have to be wrapping up. Let me go to conclusions. And I want to say that every method has a benefit in a particular application. And they help validate testing. Real errors can be found. But importantly, they are useful if they are used by someone who knows how to use them. And if they're used all together, because sometimes static analysis tools get put on the shelf and just gather dust there. For the tests to be used, it's important that they were easy to use and the results were straightforward and with a minimum number of false positives, which is quite obvious.
Кроме того, они должны быть понятны.
And they have to be understandable for engineers. And we can recall Greg Hartman asking engineers, why do you have so many errors in your kernel? And so Greg responded to that individual that engineers too skilled to do that. And normally you would put interns to debug those, and unless you change that, there won't be a lot of improvement. So the situation has evolved a lot in the past 15 years. A lot of new continuous integration systems came up, starting from kernel bots from Intel and Google Sysbot that work quite well and can detect at the level of sending patches to kernel and can give feedback to the developer. There are some testing systems, kernel CI. Some companies have their own testing systems, Huawei and Alibaba, that seem to work. And what do we have? And here we have some progress. Last year, there was the Technology Center for Studying the Linux Kernel Security was set up, which I'm a part of. And if we were to try and inspect the kernel on a standalone basis, we wouldn't get, or we would get much better effect if we were to team up and join our efforts. And quite a lot of companies have joined this initiative. For more than a year now, we have a good process of static kernel analysis and testing. Let me share some numbers. More than 8,000 warnings, alerts were followed up. 154 patches were prepared and made it to the kernel implementation. The alerts that were not confirmed, which were false positives or no fix is required, for each of them, a comment is written and every comment is cross-validated. And the quality of following up on the alerts is guaranteed in such an approach. So this idea has demonstrated good performance for a year's time, and now we started rolling it out to the user space. And here's the list of the initiatives that we started working on. And finally, I want to invite you to join this initiative. You must have open source components, and certainly you do something with the Linux kernel. And thank you very much for your attention.
Я боюсь, я слишком много говорил, нет.
I'm afraid I spoke too much, but I think I can take a couple of questions. Yes, good evening. I have a question on your framework. You said that in 17% it doesn't give results. The timeout was some 15 minutes. So my question is, what's to be done for it to give results? Answer: well, there's not much you can do. We set the timeout for 2 hours and nothing changed. So it ends up in some more difficult pieces of code where complexity grows exponentially, and you can't approach that with simple methods such as brute forcing. Thank you for the presentation. An excellent one. I have a question on the first section. Drivers are good. What about syscalls? If we do the same presentation with main, etc., and if we do security hypothesis validation, do you think that would work? Theoretically, yes, but the output could be less because the code of syscalls there's less of that than the code for the drivers, and it's in general better written. So I guess that the output would be lower, but it is quite realistic. And a question on section 3. Would it be easier, rather than manually write that automation, to use phasing, and then you wouldn't have to write anything? Sounds great, but the more challenging areas you wouldn't be able to address with just phasing. Thank you. Let's take one more question. Thank you for your presentation. At the end of the presentation, you said that you label traces. Have you tried to apply artificial intelligence to look at the remaining traces automatically? Well, the short answer is no, we haven't tried it. But an experiment can be done. What if a developer writes a module and tries to build it into the kernel, and that could lead to catastrophic events such as kernel panic? Is it possible to test the integration of the module into the kernel so that it doesn't crash? Answer: is your module binary? Well, I don't think we have any new answers to what's available in the industry. If this module is available as a source code and you can apply the tools that are available, the static analysis that I talked about, other tools that are available open source, then you want to do testing with sanitizers on. I guess the standard practice, the standard approach would be the best solution. But that's not at the level of the binary module, and you want to test it before you integrate it into the kernel. Thank you. We have one more question here. Good evening. Thank you for the presentation. And this is which version of the kernel? Which version of the kernel did you use? Because Cube T3, well, that's a separate point. I think 5.10 was supposed to become the common kernel, but now we have 5.15. So you did this on which version? 5.10 was the main version for this period. We want to add one more version to look at. And currently a consortium of companies being formed which are interested in participating. And the Coordination Council, based on that consortium, would decide which other version to add. Question: so a consortium would look at that? Answer: we'll use tools for multiple versions of the kernel that would be of interest for the participants of the process. Thank you. Okay, sorry, I guess that's it for today. And I was supposed to say that at the end there was a QR code for a survey, but it seems that I didn't even have the time for that. And I guess I want to pick the first question as the best one for the optimism, meaning if we add more time, maybe the situation would be better. Okay, so the author of that question, can you please come up here? And thank you very much.